We're going to talk about the runtime of the algorithm that we saw in the last video, which was the one that had to do with the finish first algorithm, where we're going to be picking events to maximize the total amount of events we can do. In this case, it was renting out a bike. To make sure we can rent it out to the most people possible, we are picking the events that finish first, so the ones that finish the earliest or the ones that start the latest. Both of those were symmetric. They both yield the same outcome. So we'll just look at the first iteration of that because it's going to be the same thing both ways. So we want to take a look at the runtime here to try to see, are we actually saving time by using the greedy algorithm, as opposed to, because the only other way we could have gone about that was just a brute force method where you're just trying every single outcome. And we're going to see that the runtime for, the finish the earliest, right? So finish earliest algorithm was the greedy one, obviously. And the runtime will have, so will of theta n squared. So it's going to be quadratic time. Now, this, from all this here, we know that inside of there, we're going to need to take big O n log n for sorting. Because we did need to sort the information that we had based on the way that it's arranged, right? Or the way to make sure that we have it so that the start times or the finish times, whatever we're doing, would be in order. Because obviously we do need to have some sort of order if we're going to go about doing that. So this is the way we would do it. And essentially we'd have the inner loop was being repeated n times, and then each update would apply an n amount of time, right? So that's how we get to here. So the way we arrive at the n squared over here is that we have n iterations of the loop, each taking n time, or big O of n time. Each taking big O of n time. Now this is going to be an improvement on the brute force method. Sorry, I have hot chocolate here, and if I don't drink it, it's going to have that skin on top, and so I will have a few sip breaks during this video. If we just went and did it, the absolute most primitive way, which would just be, trying every possible opportunity, right? So the brute force, every opportunity method, every possible outcome. Would be 2 to the power of n. And the reason why we'd have 2 to the power of n is because you have to try every possible outcome where you have 2 options for each one. So this would be, doing this 2n times, all this will sum up to 2 to the power of n, the n being the number of people who want to board the bike, of bike reservations, I guess I can say, bike reserves, and your options. So option to either include or not include. So we see that this would obviously be horrible. We know that stuff that is in exponential time is going to be the worst. It's going to be absolutely terrible. And in fact, it's actually going to be slower than this, right? It wouldn't just be in 2 to the power of n time, which would already be a disaster. It would actually be in 2 to the power of n multiplied by n squared time. This is going to be like an absolute disaster. So going about it that way would have not worked. So we already see that just using the greedy algorithm, we are saving time. Now the problem is big O or theta of n squared time is not that good, right? It's okay, but another sip break, I'm sorry. It's really good. I love hot chocolate. It's not the best, right? We know we can probably get better. We know that there's all these tricks that we know so that we can manipulate this to be a little bit better. So how about, this is how we're going to do it. We're going to try to make that algorithm quicker. What we're going to do is we are going to store the start and finish times together. And then we are going to go through them in order. So we go through the elements in order. And then what we'll do is if I, and I'll show you what this is in a moment, is selected, Then the next activity to be selected is the first J, and these are going to be key for the start and the stop times. We reach whose start time Sj is going to be greater than or equal to Ti. In this case, Ti will be the finish time of the first. So Sj will be after Ti. So this will be first after this guy over here. So we see that there's going to be, with this little pairing that we're going to do, we're going to be able to save some time. And this might seem a little bit strange. So let's go ahead and actually get some numbers out here so we can actually try to make a bit more sense of this. Let's get a bunch of numbers here. We will have 3, 4, we will have 7, 9, 10, 11, 13, 15, 20. We see that these are sorted. And we are going to put the corresponding values here. So these are going to be T1, T2. These are finishing times. T4, T5, T6, T7, T8, T9. Now we're going to use these in tandem with the starting times in order to save some time overall. Oh yeah, I'm sipping that close to the microphone so you can be jealous, because it's pretty fucking awesome. So now we're going to have the start times, and we said we're going to have these stored with the finishing times. So the T is the finishing times, and the start ones will be over here. So we'll have the corresponding start times here: 2, 2, 1, 8. What do we want? 6, 9, 8, 10, 12. And I'll go ahead, just to make sure it's all clear, I'll go ahead and write the corresponding values here, or corresponding symbols. 7, S8, and then S9. Okay, so what we're going to do is we are going to be starting. We have to remember, right? We have our finish times and we have our start times. Now, for this one, we'll be thinking about the one where we pick the ones that finish the first, right? The T values are the ones that finish the earliest. So we see here that what's the one that finishes the earliest over here? It's going to be this one over here. So 3 is going to finish the earliest, which means we are going to want to find a start time that is going to be able to be used, that's going to correspond to that. It'll be one that we can actually use. So what is that first one going to be? So we're going to look. Okay, so we finished our first activity. We finished it at 3. That was the earliest finishing time. So can we start an activity at 2? No, because we finished at 3. Can we start an activity at 2? No, obviously not. Can we start an activity at 1? No, it doesn't matter. So these ones over here, we're crossing them off as well, because we know that these are all going to be hooked up. Obviously this one here, I shouldn't have crossed off that 2, because that doesn't make much sense, because it was connected to the other one. So mind my blunder right over there. Go ahead and restore that. So then we keep going down here. Can we take an activity that is starting at 8? Well, yes, we can, because this is after this time over here, and this is going to correspond to the next activity that starts the earliest, or finishes the earliest. Sorry. So it's going to be the one that's still going to agree with our greedy algorithm. So we managed to just skip over these. We don't even have to compare the whole thing. We don't have to go through the whole process. So we save some time. So we are going to accept this one over here. So we will accept it, which means we are going to take this guy over here. And now we're going to compare that finishing time of 9. So we took an activity that started at 8 and ends at time 9. Now we have to keep going down here until we find another one that will work. So we are going to cross this one off. Let me get the right color. Cross this one off, cross this one off. This one down here we can accept. We can accept one that is starting at the exact same time. We assume that, for instance, this one over here with the 9 is going to finish like a millisecond before the actual time 9. So we can actually accept another one that starts at the exact same time. So in that case, we can accept that. We can go ahead and we will accept the 11. Then we will keep going down here. We will not be able to take the 8 because 8 is going to start sooner than 11. We cannot take the 10, so we cannot take the corresponding values up here, and we can accept the 12, which means we can accept the 20 all the way up here. So there we have our times, and we saved time by doing this. We didn't have to make all the same comparisons. By having these start times and these finish times paired up together, then we are able to just make a quick comparison, right? We can judge from the start time whether or not there's any chance we are going to be able to use that corresponding finish time for our algorithm. So it might seem like a bit strange of a concept, but it's going to have a good use, right? Because now what's our runtime is going to be increased. Let's go ahead and write this. Runtime will be increased to n log n plus n. And this is going to be quicker than the polynomial time of theta n squared. So we do have the n log n because we are doing lots of sorting, and then we do have the n because we're doing some comparisons. But all in all, this is going to be quicker than big O or of theta of n squared. So we do improve some time. So it's a bit of a crazy concept. If you had trouble understanding this, leave a comment below and I'll be happy to help you guys out because some things like this do get a little bit confusing, but this is just how we make problems better and better, right? We look at the algorithm we have and we say, is there any possible way that we can make this even better? Although the greedy algorithm that we found that worked was quicker than the best, the next leading brand or whatever, there's still a better way to do it. We always want to keep getting more efficient, and this is how we do it. So thanks for watching, and I'll see you guys in the next video.